Welcome to the class. We have seen that the overview of thermodynamics through different laws, and then we have seen what are the different terminologies in the thermodynamics. Specifically, we will deal in this class for the examples which would deal with the review of thermodynamics. Practically in those examples we will focus on the control volume analysis or flow processes. This is very much required since the components which are going to be studied for the gas turbine power plant, each component would be a flow process based component. Hence the analysis of that component can be well understood with the base what we would be constructing through these solved examples. So let us work out with the examples. So first example says that air at 10 degrees Celsius and 80 kilopascal enters into the diffuser of a jet engine steadily with velocity 200 meter per second. Inlet area of the diffuser is 0.4 meter square. Air leaves the diffuser with very small velocity compared to the inlet. Find out mass flow rate and temperature of the air leaving the diffuser. So let us see what are the given things here. So first given thing over here, so we are working with a diffuser. So let us plot a diffuser. Diffuser in general is a divergent area section for us. We are dealing with very low speeds. So for very low speeds the diffuser is a diverging section. So this is inlet of the diffuser, station 1, this is outlet of the diffuser, station 2. So we are told that P1 is equal to 80 kilopascal and T1 is equal to 10 degrees Celsius, which is equal to 283 Kelvin. We are also told that V1 is equal to 200 meter per second and inlet area A1 is equal to 0.4 meter square. We are told to find out the mass flow rate, which is m dot, and we are told to find out T2. So these are the two things which we need to find out. So we can know that mass flow rate is equal to rho A and V, and we will calculate everything at station 1. So that means rho 1 A1 V1. This is a steady flow system, so this has to be equal to rho 2 A2 V2. But in this formula we know that A1 is given, V1 is given, and we don't know rho 1. So let us first find out rho 1. From perfect gas equation we know that P is equal to rho RT. So P1 is equal to rho 1 RT1, and this leads to rho 1 is equal to P1 upon RT1. So that means P1 upon RT1. So P1 is 80 into 10 to the power 3 kilopascal. For air we know R is 287 joule per kg Kelvin and temperature T1 is given as 283 Kelvin. So rho 1 from this comes out to be 0.9849 kg per meter cube. This we can use to find out mass flow rate. So this is equal to 0.9849 density into area 0.4 meter square into velocity 200 will give us mass flow rate, and then that mass flow rate turns out to be 78.79 kg per second. So this is what one of the expected answers, and for this answer to arrive at we used mass conservation equation. We got this answer using mass conservation equation. For steady flow analysis always, or for flow process, we cannot just use energy equation, we also have to consider most of the times the mass conservation equation also. However, mass conservation has to be considered before considering the energy equation. So now let us apply energy equation between the station 1 and 2. So we know that steady flow energy equation is m dot into h1 plus v1 square by 2 plus gz1 plus q in is equal to m dot into h2 plus v2 square by 2 plus gz2 plus w out. We are working with the diffuser, so for the diffuser we have q in is equal to 0, w out is equal to 0. Further, change in kinetic energy is equal to 0, change in potential energy is also equal to 0. So we get m dot h1 plus v1 square by 2 is equal to m dot into h2 plus v2 square by 2. So here we can cancel m dot. Further, it is also told that air leaves the diffuser with very small velocity as compared to inlet. We can treat v2 is equal to 0. So we have h1 plus v1 square by 2 is equal to h2. So we can write cpt1 plus v1 square by 2 is equal to cpt2. So t1 plus v1 square by 2 cp is equal to t2, and then we know t2 thus is equal to 283 plus v1 is 200 square divided by 2 and to cp 1.005 into 10 to the power 3 kilojoule per kg Kelvin, and this leads to the outlet temperature of 302.9 Kelvin, which is 29.9 degrees Celsius. So this is the other example, this is the other output of the example, and this has been obtained using the energy equation. Now let us move to the next example. It states that air at 280 Kelvin and 100 kilopascal is compressed to 600 kilopascal and 400 Kelvin. Mass flow rate of air is 0.02 kg per second and heat loss during the process of compression is 16 kilojoule per kg. Consider the change in potential and kinetic energy to be negligible in the process of compression and find the power input required for a compression. So here we are talking about a compressor, so we will draw a compressor. Here it is station 1, here it is station 2, and this is a compressor, and then the given things in this example are T1 is 280 Kelvin, P1 is 100 kilopascal, P2 is 600 kilopascal, and T2 is 400 Kelvin. Further, it is also told that mass flow rate is 0.02 kg per second and heat loss in the process of heat loss, I will write it as a specific small q is equal to 16 kilojoule per kg. So we are supposed to find out what is the W in the process of compression. So let us apply the energy equation. We will write down the same energy equation, m dot steady flow energy equation v1 square by 2 plus gz1 plus q in is equal to m dot H2 plus V2 square by 2 plus ZZ2 plus W out. This is a general steady flow energy equation. Now in this case W out is 0. We are again not going to consider any change in kinetic and potential energies. So we will have m dot H1 plus Q in is equal to m dot H2. Okay, sorry, we are supposed to find out W in. So we are working with compressor, so we need W. Only change in potential and kinetic energy is neglected. So we know m dot, and m dot is 0.02. H1 is Cp into T1 plus Q1 is m dot into Q, and then this is heat loss, so it will have negative sign. Then we have 0.02 into Cp into T2 and then plus W out. So W out will be minus 0.02 into 1.005 into 10 to the power 3 T2 minus T1 minus m dot is 0.002 into 16 into 10 to the power 3 kilojoule per kg. So W out is equal to 0.02 into 1.005 10 to the power 3 T2 is 400 minus 280 minus 0.002 into 16 into 10 to the power 3, and then this answer will be 2.2732 watt. Negative sign indicates that work output is negative, that means work in is positive and it is 2732 watt, or it is equal to 2.732 kilowatt. So here in this example we just needed to find out the work output, and then that needed only the energy equation. So we will move to the next example, and next example says that helium is compressed from 20 degrees Celsius and 100 kPa to 315 degrees Celsius and 1400 kilopascal. Outlet area and velocity are given, which are 0.001 meter square and 30 meter per second respectively. Inlet velocity is 15 meter second. Find out mass flow rate and inlet area. R for helium is given as 2077 joule per kg Kelvin. Again this example deals with compressor, so we have 1 at the compressor inlet and 2 at the compressor outlet, and we will note down the given things for us. So given things include T1 is 20 degrees Celsius, so it is 293 Kelvin. P1 is equal to 100 kilopascal, and then we are said that P2 is equal to 1400 kilopascal and T2 is 315 degrees Celsius, which is nothing but 588 Kelvin. We are also given that A2 is 0.01 meter square and V2 is equal to 30 meter per second. We are told that V1 is 15 meter per second, and then we are supposed to find out m dot and area at inlet. Okay, as we had seen in last example, we need m dot. We know m dot is equal to rho 1 A1 V1. In the steady flow case it is rho 2 A2 V2. In the present case we know A2 and V2, but we don't know rho 2. So let us find out rho 2 is P2 upon RT2. P2 is given 1400 kilopascal divided by R for helium is 2077 into temperature, which is 588 Kelvin. So this gives us density for the helium at the outlet, and then that is 1.146 kg per meter cube. We can as well find out density at the inlet, which is P1 upon RT1, and then that is 100 kPa divided by 2077 into inlet temperature is given, which is 293, and inlet density is 0.164 kg per meter cube. Knowing this, we can find out mass flow rate, which is 146, density at the outlet into velocity at the outlet is 30 into area at the outlet is 0.001. So we get m dot as 0.034 kg per second. So this is one of the answers which we got from the mass conservation equation. Now we know equation as rho 1 A1 V1 is equal to rho 2 A2 V2. We are interested to find out A1. So A1 is equal to rho 2 A2 V2 divided by rho 1 and V1, it is 0.034 divided by rho 1 as 0.164, and V1 is 15, and this comes out to be 0.0139 meter square. So this is the area at the inlet, and this is also evaluated by us using only mass conservation equation. So we have to see which equations are important for solving the example in case of steady flow, and then we might need both area and mass conservation. We might need energy and mass conservation, or we might need either. So next example states that stators of a gas turbine are designed to increase the kinetic energy adiabatically. In the example, it is stated that it is adiabatic. So adiabatic means there is no heat interaction. So it is given that Q is 0. Air enters the stator at 370 degrees Celsius, 2100 kPa and velocity of 25 meter per second. Exit conditions are 1750 kPa and 340 degrees Celsius. Calculate velocity at the exit. So as per the example, we are working with a nozzle, since it is a stator of the turbine. So this is 1, this is 2, and then we are given that gas is air, and then T1 is 370 degrees Celsius. So it is 643 Kelvin. P1 it is 2100 kilopascal, and then P2 is 1750 kilopascal, and T2 is 340 degrees Celsius, which is basically T2 is equal to 613 Kelvin. So we are supposed to find out what is velocity at the exit, since we are given that velocity V1 is 25 meter per second. Here we are not needing anything related to mass conservation equation. So let us apply energy conservation equation between the station 1 and the station 2. which is a steady flow energy equation. Let us consider steady flow energy equations between station 1 and 2. This is a stator of the turbine, so it has no work interaction. We are said that process is adiabatic. In this case, m dot would cancel, and we are obviously having no potential energy change also. So we have H1 plus V1 square by 2 is equal to H2 plus V2 square by 2. So H1 is CPT1 and then it is V1 square by 2, H2 is CPT2 plus it is V2 square by 2. So Cp is 1005 into T1 is 643 plus V1 is 25 square divided by 2 is equal to Cp 1005 into T2, and T2 is 613 plus V2 square by 2, and then this gives us V2 is equal to 246.82 meter per second. So we just used only energy equation to solve this example. Now move on to the next example. We state that air at 600 kPa and 500 Kelvin enters an adiabatic nozzle which has inlet to exit area of 2:1. Velocity of the air at the entry is 120 meter per second and at the exit is 380 meter per second. Determine exit pressure and temperature. So since we are told that it is a nozzle, so for us low speed nozzle is a converging duct. So let us consider two stations 1 and 2. For the nozzle it is adiabatic. So given things in this example, our gas is air, entry is 600 kPa, temperature T1 is 500 Kelvin. We are told that A1 by A2 is equal to 2, and V1, which is velocity at the inlet, is 120 meter per second, and velocity at the exit is 380 meter per second. We are supposed to find out P2 and T2 are the question. So let us apply the first energy equation over here. H1 plus V1 square by 2 plus GZ1 plus Qin is equal to m dot H2 plus V2 square by 2 plus GZ2 plus W out. So this is a nozzle, it is an adiabatic nozzle, so no heat interaction. It's a nozzle, it has no work interaction. We further don't consider any potential energy change. So we have m dot getting cancelled. So we have H1 plus V1 square by 2 is equal to H2 plus V2 square by 2. So CPT1 plus V1 square by 2 is equal to CPT2 plus V2 square by 2. So this leads to the fact that T2 is equal to T1 plus 1 upon 2 Cp V1 square minus V2 square, and hence putting all the numbers we get T2 is equal to 500 Kelvin plus 1 upon 2 into 1005. V1 is 120 square minus V2 is 380 square, and then this gives us T2 as 435.32 Kelvin, which is equal to 162.32 degrees Celsius. So this is one answer which is obtained by us based upon energy equation. So now we need to find out pressure. So for that we will apply mass conservation equation, which says that m dot is equal to rho 1 A1 V1 is equal to rho 2 A2 V2. So then we know that rho is equal to P upon RT1 into A1 into V1, where rho 2 is equal to P upon RT2 into A2 into V2. RR will get cancelled. So we have P1 A1 V1 upon T1 is equal to P2 A2 V2 upon T2. We are interested in P2, and then P2 is equal to P1 into A1 by A2 into V1 by V2 into T2 by T1. So we know that P1 is given to us, which is 600 into 10 to the power 3. We are told that A1 by A2 is 2. We are told that V1 is 120 meter per second and V2 is 380 meter per second. We got T2 as 435.32, and we know T1, which is 500 Kelvin. And then this leads to P2, and then that P2 is 329926.73 Pascal, or P2 is equal to 329.92 kilopascal. So the second answer what we got for this example is based upon the mass conservation equation. So this is how we are coming to know that we need mass and energy, both conservation equations, to be applied for solving a particular equation or particular example of steady flow process. Let us move on to the next example. It states that air at 80 kPa and 27 degrees Celsius enters a diffuser at 220 meter per second with a mass flow rate of 2.5 kg per second and leaves at 42 degrees Celsius. Exit area of the diffuser is 400 centimeter square. Air loses heat at 18 kilojoule per second. Determine the exit velocity and pressure. So for this example, again we are working with a diffuser. For low velocity, diffuser is a divergent section, and we have one for the inlet and two for the outlet in case of the diffuser. And given things for us over here are P1 as 80 kPa, T1 as 27 degrees Celsius, which is 300 Kelvin, and we are told that V1 is 220 meter per second. We are told that m dot is 2.5 kg per second. T2 is equal to 42 degree Celsius, and which is basically 315 Kelvin, and we are told that A2, which is exit area, and that is 400 centimeter square, which is 400 into 10 to the power minus 4 meter square. So let us apply again energy equation, steady flow energy equation. H1 plus V1 square by 2 plus GZ1 plus Q in is equal to m dot into H2 plus V2 square by 2 into GZ2 plus W out. We are working with diffuser, so this is ruled out. There is no work interaction. We are again given with Q out as 18 kilojoule per second. so 18 kilojoule per second. So m dot is known to us, which is 2.5, H1 is CPT1 plus V1 square is given to us. We are neglecting the potential energy change, plus Q in is equal to m dot, which is again 2.5 into CPT2 plus V2 square by 2. So let us work out. We can find out here 2.5 into 1005 into T1 is 300 plus V1 square is 220 square by 2 plus basically heat is lost, so that is minus 18 into 10 to the power 3 is equal to 2.5 into 1005 into T2, which is 315 plus V2 square, and V2 we are interested to find out. If we solve this equation, we will get V2, and then that V2 is 62.04 meter per second. Since it's a diffuser, exit velocity is lower than the inlet velocity. So we got this answer from energy conservation equation. We want pressure to be found out at the exit. We know that m dot is equal to rho 2 A2 V2, and then this is 2.5 kg per second. So where rho can be written as P upon RT2 A2 into V2. So we know pressure at the exit of the we are supposed to find out pressure at the exit of the diffuser. So we know that P2 is equal to 2.5 into R into T2 divided by A2 into V2. So 2.5 into R is 287 for air, T2 is given to us, which is 315 Kelvin, divided by area, which is 400 centimeter square. So that is 10 to the power minus 4, and V2 we have found out, which is 62.04, and this gives us pressure as 9.10 into 10 to the power 4 or 91 kilopascal. So we got the second answer of this question based upon the mass conservation equation. So we have to remember here that how to apply the mass and energy conservation equations for the different components like compressor, diffuser or nozzle, stators, rotors, and these are the basically components for a gas turbine power plant. We need this understanding while deriving different performance parameters for the gas turbine components or gas turbine power plant in general. I hope this will help us for getting those desired equations or the values. Thank you.